Hey there. So, I am going to be building a little C# program today for calculating the value of pi. Picking C#, most of my work lately has been in C#. So it's good to practice. But I use Visual Studio Code, partially because I'm in Linux, partially because Visual Studio Code is just a lot lighter weight than Visual Studio. Alright, so need to create a new .NET project. What am I going to call this thing? Just call it Pi Calculator. Default directory is fine. Create project. And it added another solution next to my solution. Let's see if I can just port this over. I want to call the solution just pi, but I'm not sure how much I care. You know, I don't care. Out with the old solution, in with the new one. So, we have a little program that we're going to use to calculate the value of pi. And go to terminal, .NET, run, can't find a project to run. Project, Pi Calculator. Now, got our hello world program. So, we're in .NET, and the default template is terrible. So, go away. Namespace, Pi Calculator. Create a program. Much better. So, the easiest way, of course, to calculate the value of pi in .NET is to simply hold on. Math.pi. Well, there you go. There's the value of pi, if you want to keep it simple. Which, of course, I don't, which is the only reason I'm recording this video. But we'll keep it there anyway. So, this value is a double, which is a 64-bit floating point number. There's 3 types of floating point numbers in .NET. Short, which I believe is a 16-bit floating number. Ah, no, it's a signed integer. I guess wrong. It's been too long since I've done this. Got the single precision floating point number, which is also aliased to just a float. And then you have the double. And there's also a decimal, which is the longest form of a floating point number, which is usually used for like bankers math. Decimal floating point number, that description is not useful, but basically it gives you twice as much precision as a double. Okay, but the point is that there's only so many points after the decimal point that you can shove into a double, and after that it starts getting into exponential notation. So let's see if we can calculate pi. I'm starting with Wikipedia. What does Wikipedia have to say about pi? Well, if you're watching this video, you already know what pi is used for. So we can skip over that part. Pi is irrational, which basically means that there's no end to the digits in it. Oh, well. It cannot be written as a ratio of 2 integers. Well, sure. Okay. And comes up in a lot of math. And basically, the number of digits in pi, at least in base 10, seems to go on forever. But there's various ways of approximating it. Any time you see pi written out, just whether it's 10 digits or a million digits, it's still an approximation, which is just so weird. And, there we go. Calculation of pi, revolutionized by the development of infinite series techniques. Well, let's grab one of these infinite series. Viète's formula. Let's try Viète's formula and see how it goes. The infinite product, square root of 2. Let's see, how would you represent that with a C# program? But let's try representing this. Of course, it's not the best algorithm because there's 1593. A lot of other algorithms have come out since then, but it's something to start with. So, until this thing just go on forever. Now, how could we represent this? I don't know if I'm going to actually follow through with this one or not. I am struggling to figure out how you would represent that in any sort of loop. Square root of 2 over 2, and then the next loop is let's see. Okay. First of all, I can already tell you we're going to need to pre-calculate the square root of 2. And then we need a loop counter. And then we're going to need an inner loop to account for the numerator for this round. Let's say the numerator equals 2. And then numerator equals whatever was in there's almost certainly going to be a problem with this. This is all working with doubles. So the square root is a double, takes a double, returns a double. The counter can be an integer. The numerator is going to be a double. So 2 plus the square root of whatever the previous answer was, which seems to represent what's going on here. And then divide that whole thing by 2. Now, that's actually the inverse of pi, sort of. How in the world did François Viète come up with this? He must have just really loved square rooting things. Okay. So we're dividing the numerator by 2, and then we have to multiply it by the previous numerator. So let's grab that. And it needs to be 1, because if the initial numerator is 0, multiplying by it will give us diddly squat. No, I want it down here. Actually, we don't need the previous numerator because I think we can do this. I think. Oh, no, we do need it because... No, we're going to continue along this path, and then there's ways to optimize this that we're going to get to soon. Just want to see if this even calculates the right thing, though. This thing's never returning. We're just going to void that out. And actually, we're not taking any args right now. Okay. Now, theoretically, at this point, we should have the inverse of pi. This is going to break because I'm going to tell it to break. And we don't need to store the square root of 2 because the way this works, it doesn't really help us. Alright, let's see what this gives us. It'd be a miracle if it gives us anything. Oh, I actually have to write out the result or it doesn't count. Call this Viète's pi. Oh, I want to have that little... Those accent marks matter. Too many words, it just becomes a completely different word if you don't include the accent mark. So the actual value of pi is... You have to invert the value and then multiply by 2. So... That's how we'll do it. Now let's see if we properly calculated Viète's pi. Ooh. It's infinite. That's not right. For the first one, let's look at this again. Inverse pi when the counter is at 0, It's going to start with 2 plus the square root of 2. But it's missing the first section where it just has square root of 2 over 2. Square root of 1 is 1, right? Yeah, square root of 1 is 1. Let's start this at 1, and then on the first iteration of the loop, it'll be 2 plus, well, 1. It's wrong also. You know what? Let's initialize this to the square root of 2, and then it'll still be wrong. I think. Two plus the square root of anything that came before. Square root of 0 is 0. I can do that. Just want to make sure. First iteration, 2 plus the square root of 0, so it's just 2. And then the next iteration, it'll be 2 plus the square root of 2. And then the next iteration will be 2 plus the square root of 2 plus the square root of 2. And when it's done creating the sum for the numerator, it'll divide by 2. And then increment the counter, multiply, but why whatever came before. That needs to be 1. Otherwise, we're multiplying by 0 forever, which is useless. Okay, let's try again. Still infinite. Here. We'll output on each iteration. What is going on with my sum? Well, it starts off infinite, skips every other iteration. We don't need that sum twice because it's also summing in the for loop. Okay, starting from 0. Whereas the infinity let's get the value of the inverse of pi. It's just 0. We're doing 2 over 0, which is infinity. Why is that 0? Because the numerator starts at 0. Counter is starting at 0, so as long as 0 is less than 0, it's not 0 is equal to 0. So in the first iteration of the outer loop, the inner loop never executes. Numerator stays as 0, which then loads 0 into the inverse of pi. Cool. Let's try that. That's at least giving us a number. That's an improvement. It's the wrong number. How long does it take this thing to coalesce? Alright, Viète, what were you thinking? So we calculate the top, and then we divide by 2. Do this manually, and then we'll figure out how to improve it. The problem is that numerator. And then okay, trying this manually. You make sure we're actually multiplying out the product. Let's see what that does. That is actually giving us something that looks pie-ish, pie-shaped. So that's cool. How do we turn that into a loop? On each of these blocks, the product is doing the exact same thing. Multiply it by the numerator, divide by 2. Numerator is doing the exact same thing on every one except for the first. Okay, that is looking better. Now that is something that we can put in a loop, because it's doing the exact same thing every time. One, two. So add some space here to line them up. I think that's right. Like that. Maybe. don't need to report that anymore. Now, I'm going to assume that the built-in value of pi is more accurate to that number of digits, so ours is off. Theoretically, we run the loop more and we get closer to pi. Dumping all this, it's wrong. Don't need it in our life. Let's go out to 100. 9.4 instead of 9.3. All the other digits are right. How far do we have to go out to fix that? Still 9.4. This is probably a bad idea. Yeah, that's a bad idea. Okay, not using the max value. That is... We'll go to 1 million. Now this raises another question. What is the actual value of that last digit? Here. 1 million digits of pi. 3.1415926535897 It should not be 94. It should be 93. So why is it getting weird about that final digit? And it's, I don't know, probably some sort of internal rounding error. How do we represent a decimal? This is something that we can do because we're actually calculating pi ourselves. Right. That makes it a decimal, or a double. How do we make it a decimal? Well, we can always do this. Oh, M for money. Oh, but the problem is square root is still working with doubles. There has to be some way to do a square root with decimals. So I'm sure there is, but I'm not seeing it here. So we're going to take this to as much precision as the algorithm will allow us. And since I cannot take the value square root of a decimal in a way that I can locate right now, and there's not much more we can do with it. It does seem to get to its solution pretty quickly, though. At least for that number of digits. Which is probably good, because when Viète first did this, he didn't have a computer. He had to do this whole thing by hand. Ancient mathematicians are just that cool. We'll keep the counter at 30. One more run, and looking this over to see if there's anything I can do to speed. There may or may not be a way to speed this up, but I'm not even sure that it matters because it runs so quickly for that number of digits. I would love to get more digits. I'd love to have a program that will dump out like pi digits forever. At least 1,000,000 digits I was just showing you on that other site. But I'm going to stop there for now. We'll have to be satisfied with Viète's pi for today. And next time we will find another pi, or a more accurate pi. And that is all. Thanks for watching.